Welcome to qnawire.
So we have a ring of mass capital M and then a smaller mass a distance x away from the center of the ring. And we want to find what the potential energy of this system is. So we know in general that potential energy is negative g and then the two masses divided by r. But whenever we have a distribution of mass, so something like this ring that isn't just a point particle, usually we'll need to integrate to find what the potential energy is. So to start then, we want to write down what du is, the differential potential energy that's made just by a small differential piece of this mass dm. So just an infinitesimal part of this ring should make a potential energy du, and that then should be negative g, little m, and then times that differential piece of mass, and then divide by r. So then to find the potential energy, we want to integrate that with respect to dm. So negative g m over r dm, and then the integral of this whole thing. So a lot of times then what'll make this tricky is that dm will depend upon r. So the amount of mass you have will depend upon the distance away from the mass. But what's nice here is that everything is pretty symmetric. And so if we write out what r is actually going to be, we can see that any little piece dm of this ring is going to be the same distance from lowercase m here. So any spot will just look like this. So it's always going to be making a triangle where one leg is x and then the other leg is just the radius of the circle. So our total distance then is always just square root of a squared plus x squared for any little piece of the ring going to the test mass. So then our integral becomes negative g, little m, and then r is square root of a squared plus x squared, and then dm. And so then dm doesn't depend on a or x at all. And so when we integrate this, dm just becomes m. It's just like integrating a constant with respect to m here. So this just becomes then negative g, little m, capital M, over square root of a squared plus x squared. And so we can see then this answer gives us a potential that's going to be a little bit smaller than if this ring of mass was just concentrated at the center. So basically parts of the ring pull up on the mass, parts pull down, and those will be canceling each other out. So we end up with a slightly smaller potential term because this a squared is in the denominator. So there's our potential energy. And then in part B, we're asked to show that this reduces to the expected result if x is much bigger than a. So typically when we have the distance between two things become very, very large, this test mass no longer really sees in some sense that this capital M mass is like a ring. It just sort of looks like a small dot from far away. And so that's usually what we expect to happen in these cases. So part B then, we can see that if we have x being much bigger than a, then this denominator just becomes square root of x squared. So we basically get to ignore the a squared. So then we have u equals negative g, little m over square root of x squared. And that, of course, just becomes x on the bottom. So this looks exactly then like we'd have for potential if we just had 2 point particles, one with mass little m, one with mass big M. And so that's what we expect to happen when we have the separation between the two becoming very, very large. The radius of the circle and like the actual mass distribution no longer matters, only the total mass. So for part C, we'll go on to a new page. And C asks us to find what the force in the x direction is due to the potential, and they want us to find it in this manner by differentiating the potential. And so really this is going to be the total force because the situation is so symmetric, it's pretty easy to see that the y forces will cancel each other out. So we want to start setting this up. So we'll have negative and then d by dx of u, and we just found that u was negative g little m big M over square roots of x squared plus a squared. So we can pull out all these constants, so these negative signs cancel out, and so we get just g little m big M, and then derivative of 1 over square root of x squared plus a squared. So you can do that derivative using the chain rule, and you should find then that the force is going to be negative 1/2 x squared plus a squared, and that's to the negative 3/2, and then times 2x. And so we can then simplify that a little bit more and write this as negative g. Oh yeah, we forgot the g and the m's in that previous line. So negative g little m big M, and then x over x squared plus a squared to the 3/2. So there we go on that. So this was part C. And then part D, just like before, they want us to now see that this reduces to the expected result when x is much bigger than a. So same deal. We'd expect then that this is basically going to look like 2 point particles when we have the separation between them being very large. And so when we make x big compared to a, this denominator is just going to become x squared without the a there. So we'll just have fx equals negative g little m big M over x squared, but then that's still to the 3/2, and then we have an x up in the numerator too. So that 2 and that 2 will cancel. So we get negative g, and then little m big M over x cubed, and we still have an x in the numerator, and so that cancels. That becomes a 2. And so finally, negative g little m big M over x squared. So exactly the force that we expect between just 2 point particles of mass little m and big M. So, and then the negative sign tells us that this is an attractive force, or equivalently in how we've drawn this and kind of assumed with our coordinate system that little m is being pulled towards big M. And finally then part E, we'll go on one more new page. So part E wants us to evaluate the potential at x equals 0. So potential for x equals 0, that should just give us negative g little m big M. And looking at a potential term again, so we'll end up with just if x is 0, we'll just have square roots of a squared in the denominator. So that'll end up just being a. So we basically just can get the exact potential for two masses separating by a distance a, which is pretty much the situation we have here. Every part of the ring mass is a distance a from the little mass, so it ends up being the equivalent situation. And then for finding the force, so looking at our force equation, we can see then that if x is 0, we're just going to have no force. So this x in the numerator will make the whole term 0. So f of 0 just equals 0. And that should be what we expect. So when we look at this, we imagine our test mass right in the middle. There's definitely individual forces acting on it, but because this is symmetric, they're all going to be canceling out with each other. So if we put this exactly in the middle, we shouldn't expect it to have a force and have an acceleration on it. It's a very unstable equilibrium, though, because if it moves a little bit, then it'll be pulled to one part of the ring, which is why we find that there is a potential energy here.